In this video, we're going to be learning how to write the rate of the reactions using the concentrations of the reactants and the product. So let me write up a generic reaction. So suppose I have an N2 reacting with H2, and it's going on to make ammonia. That's going to be NH3. And if I balance the equation, I would need to have 3 in front of H2 and 2 in front of NH3, and that should balance out your equation. If I want to write down the rate of the reaction, I can write that down in terms of the reactants disappearance, in terms of the product's appearance as well. So anytime you are writing the rate of the reactions in terms of the reactants, you will write a negative sign. That's because over time you will lose your reactants. So I would go ahead and do minus the change in the concentration of N2 divided by the time, change in time, and that's going to be also equal to, if I want to go ahead and write that down in terms of the H2, that's going to be minus again because that's still in a reactant. And then we also got to keep track of the coefficients. Remember, your hydrogens are being lost 3 times faster than the N2. So when you're taking that into account in terms of the rate of reactions, I would go ahead and write down 1 over 3, the change in the concentration of H2 over the time. So another way of saying, if you see a coefficient and when you're writing the rate of these reactions, the coefficient goes in the denominator anytime you have them in the reaction. So if I want to go ahead and write that down in terms of, let me just move that a little bit onto the right side there. And if I want to go ahead and write that down in terms of the products as well, so that's going to be equal to the change in the concentration. So since this is actually the product now, we're going to write a positive sign there. You only write down negatives for the reactants. And since you have 2 in front of the coefficient, as in a coefficient in front of NH3, I would go ahead and write that down 1 over 2, the change in the concentration of NH3 over the time. So it's probably better if I move this down here actually. So let me fix that. It's going to be change in the concentration of NH3 over the change in time. So this is going to be your way of writing the rate of the reactions with respect to the concentration of the reactants and the products. So you want to make sure you use the coefficient. So you want to make sure you put down negative signs when you're writing in terms of the reactants and positive signs in terms of the products. So when you're writing those coefficients in the denominator, what that really means, it tells you that okay, the rate of disappearance of hydrogen is going to be 3 times faster than the rate of disappearance of nitrogen. That's because the nitrogen and hydrogen is a 1 to 3 mole ratio. So another way of saying, if I lose 1 mole of N2, I should be using 3 moles of H2. So when I'm writing the rate of disappearance of N2, that's going to be the change in the concentration of N2 over time. And when I'm writing the rate of disappearance of H2 is going to be the change in the concentration of H2 divided by the change in time. And then the rate of appearance is going to be the change in the concentration of NH3 divided by the time. So technically, if I know any one of those 3, so I have actually four things here, so I'm number those 1, 2, 3, 4. Out of those 4, if I know one, I can calculate the rest because I already know the relation among all 4 of those. So if I know the rate of the reaction, I can figure out the rate of disappearance of N2, I can figure out the rate of disappearance of H2, and I can figure out the rate of appearance of NH3. And if I suppose the rate of appearance of NH3, then I can figure out the rest using those equations. So you want to be able to write this out and be able to calculate the rest if you're given one of those. Now, if I want to roughly make the graph out of those, so suppose this is the reaction time here, And then on the y-axis, we got the concentrations. And I'm gonna say this one right there. Let's change the colors there. This one is gonna be your hydrogen concentration in the beginning because you're gonna have only reactants in the beginning, and that one is gonna be your N2. Just keep an eye on the color combination there. And then finally, that one is gonna be your NH3, the green line. Because remember, in the beginning, you don't really have NH3 because NH3 is your product. So as soon as you mix the N2 and the H2 together, what's going to happen? Their concentration is going to start decreasing over time, but the concentration of NH3 is going to start increasing because you're making the products and you're going to be losing the reactants. And after some time, they may reach so-called in a steady state, and at steady state either the reaction has been completed or you may set up an equilibrium where there is no net change in the reactions. So the equilibrium reactions, we'll talk about those later, but let me focus on a particular time here. So suppose I have a time frame here, and I can probably just draw a line here for that part. If I draw a line here, and I'm going to be looking at wherever we meet on those three graphs here, and if I draw the tangent on all three graphs, if I draw the tangent on this NH3 graph here, so this, I'm going to call this line A, and then I can draw the tangent on this N2. It's not the best tangent, but you guys get an idea there. Let's call that B. And then I have another tangent there on the nitrogen line that's going to look like this. I'll make that a little bit longer so that you can see it. Let's call that C. So the slope of these lines actually going to give you the rate or the rate of appearance and disappearance at a particular given time. So I can also say the slope of B, let's see, and the slope of A, and then we got a slope of C. So how they're going to be related with one another. So if I go back to the reaction and look at how the rate of appearance and disappearance work, you know the N2 you have a 1 in it as a coefficient, and the NH3 you have 2 as a coefficient. So what you can say, the rate of formation of NH3 is going to be 2 times than the rate of disappearance of N2. So I can say the slope of A is actually going to be equal to 2 times the slope of B, because just what we said, the formation of ammonia is going to be twice than the loss of N2 at a given time. Okay, and then I can also say the slope of C is going to be 3 times the slope of B. That's because the rate of disappearance of your H2 is going to be 3 times the rate of disappearance of N2. Now you may wonder that, okay, we got a positive slope and we got a negative slope, and how are we really comparing those? Well, yes, it is in a positive slope because you're making something, and the negative slope, you're losing something, but I'm just talking about the magnitude of the loss and the formation. So when I'm comparing the magnitude of slope of A and the magnitude of slope of B, the A is going to be twice bigger in terms of the magnitude than the B here, than the slope of B. And how would you really compare the slope of A and C? Well, in that case, I can say the slope of A is going to be actually equal to 2/3 the slope of C. And what we're really doing here again, we're still using our coefficients there. So remember, um, we know hydrogen in this particular case is going to be the one that's going to be lost the fastest because it has 3 in front of it as in a coefficient. But then when I compare the formation of NH3 with respect to the hydrogen, I know the formation of NH3 is going to be less faster than the loss of H3 just because of their stoichiometry relation. Now, how less that's going to be? Well, you can use their coefficients to figure that out. So that's what we really said there. We got 2 here and we got 3 there, and that's what we really written down there. So the slope of A is going to be related to the slope of C in terms of the magnitude by a factor of 2/3. Okay, let's look at this question here and see if you guys can do this. We're just still talking about the reaction of nitrogen gas and hydrogen gas, and you're told that the concentration of hydrogen gas was decreased from zero point 0.3 to 0.21. So what's going to be the change in the concentration of H2? Well, it's going to be 0.21. You always write down the final minus initial. So if I can maybe write down the concentration of H2 final minus the concentration of H2 initial. So I know it's going to be 0.21 minus 0.30, and that's going to be equal to 0.09, negative 0.09 molar. So what that means, in the time frame of 10 seconds, you have lost about 0.09 molar H2. Now, if I want to go ahead and write down the rate of this reaction, I know with respect to the hydrogen, it's going to be negative 1/3 the change in the concentration of H2 over the change in time. So now we actually know everything. We got 1/3. The change in the concentration of H2 is going to be negative 0.09 divided by the change in time, which is going to be 10 seconds. So we'll just do the math here, and that gives you the rate of the reaction. So that comes out to be, so the negative negative becomes positive, so it's going to be 0.003 molar per second. So remember, the concentration is going to be measured in molarity, and the time is going to be in seconds on the bottom. So seconds here and the molarity here. So that's how your rate's always going to be measured. So this is going to be the rate of this particular reaction. Now, the other type of question you are asked here is to figure out the disappearance of H2 gas. Well, what we just found here, the delta H2 over the delta T, that's going to be the rate of disappearance of H2, and we already know the H2 to be negative 0.09 here, divided by 10. So it's going to be 0.009 negative in front of it, molar over second. So that means you're losing 0.009 molar of H2 every second, basically. And then how would you find the rate of disappearance of N2 and the rate of appearance of NH3? So I can probably go back down there and maybe copy this equation so that I don't have to rewrite it. So let's bring that down. Okay, so I already know 2 things so far. I already calculated the rate of the reaction, I already calculated the rate of disappearance of H2. So what's going to be the rate of disappearance of N2? Well, if I already know the rate of the reaction, which we already calculated, I can relate these 2 terms right there and figure out what the change in the concentration going to be for the N2 over time. So divide that by delta T, so there's a negative sign, and the rate of the reaction that we just calculated was 0.003 molar per second. So if I rearrange this and get the negative sign on the other side, then it's going to be negative right there. So that's going to be the rate of disappearance of N2. So if I go back and look at the stoichiometry relation between the N2 and H2, we know it's a 1 to 3 mole ratio. What that means, the H2 should be consumed 3 times faster than the N2. So let's compare their rates now. The rate of disappearance for H2 was 0.009 and rate of disappearance of N2 is 0.003, and that's exactly supposed to be because H2 disappears 3 times faster than the N2. Okay, in addition to that, we can also figure out the NH3. So to do the NH3, you don't really have to use the rate of the reactions all the time. You can use other stuff as well. Like for example, I know the rate of disappearance of H2, so I can probably use this last two terms there. So let me just copy those down there and bring those down here. Okay, so it's going to be negative 1 over 3. So the rate of disappearance of H2 was negative 0.003. So remember, I'm getting that number from a right, it's a negative 0.009 rather. So I'm getting that number from up here, what we just calculated earlier, and that's going to be equal to 1 over 2, the rate of appearance of NH3 divided by the time, and you can just do the rearrangement there, do your math. So multiply both sides by 2, it's going to be negative 2/3 times 0.009 equals to delta NH3 over the time. So what that's going to come out to be, it's going to be 0.006. So that's going to be the rate of appearance of the NH3. So that's going to cancel out. The minus is going to cancel out, so you're going to get a positive at the end of the day. That's because you are making something, so you must have a positive appearance rate anyways. So does this look familiar right there? If I focus this on 2 over 3 times the rate of H2. Well, if I go back to that equation or the graph that we just written out earlier, remember the slope of A, which A was technically the NH3, was going to be equal to the 2/3 of the slope of C, and the slope of C was the change in the concentration of H2 basically. So that's exactly what we have down here. So the bottom line or the take-home message here is be able to write the rate of the reactions with respect to the reactants and products, and be able to identify the terms like disappearance, appearance, and how you're going to be converting among one another. All right, if you have any questions, feel free to leave any comments in the section below.